The internet is basically a giant global delivery system, kind of like a digital postal service. And its mission is huge, to let any two devices on the entire planet exchange data with each other. Today, we're going to follow one single piece of data on its incredible journey from your screen, out into the world, to a server, and all the way back. Think about it. You click a link, and almost instantly, a web page from a server that could be thousands of miles away just appears. So what's actually happening in that split second? Well, the answer is in the network layer, and it all starts with a little something called a packet. Okay, let's dive into this with a simple analogy, because it makes everything so much clearer. Just imagine the internet is one giant worldwide postal service. The data you're sending, that's your letter. An IP address, that's the mailing address on the envelope. And routers, well, routers are all the post offices and sorting centers that guide your letter along its way. With that in mind, let's see how our digital letter even gets ready to be mailed. Right? So before our data can go anywhere, it needs to be packaged up properly. You can't just drop a loose piece of paper into a mailbox and hope for the best, right? Same idea here. Your data can't just float around the internet on its own. It needs to be put into a standardized digital box. This whole process, it has a technical name, encapsulation. But really, it's simple. First, you take your data. Then, you digitally box it up inside what's called an IP packet. And then, the most important part, you slap a digital shipping label on the front. We call that the IP header, and it has all the instructions for the entire journey. So what's actually on this digital shipping label? Well, the IPv4 header has some really crucial info. You've got the destination IP address, obviously where it's going, and the source IP address, where it came from. But then there's this super clever field called time to live, or TTL. It's basically a self-destruct counter. It stops lost packets from just bouncing around the internet forever and clogging everything up. Pretty smart, huh? For decades, that IPv4 header worked perfectly, but it had one huge limitation, a kind of ticking clock that was built into its design from day one. See, the internet was growing way faster than anyone ever imagined, and we were about to hit a massive wall. 4.3 billion, that was it. That was the total number of addresses available in the original IPv4 system. And yeah, it sounds like a lot, but by 2011, we had officially run out. The internet's postal service was completely out of mailing addresses. So what do? Well, the solution was a massive upgrade, IPv6. Instead of 32-bit addresses, it uses 128-bit addresses. And that creates a number of unique addresses so ridiculously vast, it's almost impossible to comprehend. And we need them. Think about it. It's not just phones and computers anymore. It's smartwatches, smart homes, smart cars. Everything needs its own mailing address. IPv6 makes all of that possible. Plus, it even simplified the packet header, which lets routers process everything that much faster. Okay, so our packet is all packaged up, it's properly addressed, it's ready to go. But how does it know which way to go first? It needs a door to get out onto the wider internet, right? And that door is called the default gateway. Think of it as your local post office. For most of us, this is just our home Wi-Fi router. Its entire job is to be the single drop-off point for any letter that needs to leave our local network. Your computer doesn't even try to find the final destination itself. It just hands the packet off to the default gateway and pretty much says, "Here, you figure it out." And figuring it out is exactly what routers do best. A router's job is just this constant, crazy high-speed loop. It gets a packet, it reads the destination IP address, it quickly looks at its internal map of the internet, that's called a routing table, and then bam, it forwards the packet to the next router on what it thinks is the best path. And it does this millions of times a second without ever breaking a sweat. Now, as our packet is hopping from router to router, it's operating under a very specific set of rules. And this is where the philosophy of the internet gets really fascinating. You see, it's not built on perfection, it's built on speed and efficiency. This quote right here gets to the absolute heart of it. The Internet Protocol, or IP, is designed for low overhead. That means it doesn't waste time with a bunch of extra features. Its only goal is to get packets moving as fast as possible. Guaranteed delivery? Nope. That's a problem for another part of the system to worry about. So, the IP protocol basically lives by 3 simple rules. First, it's connectionless. It doesn't call ahead to see if the destination is ready to receive anything. The packets just show up. Second, it's best effort. It tries its absolute best to deliver the packet, but there are 0 guarantees. It has no idea if the packet got lost or messed up along the way. And third, it's media independent.
IP just doesn't care if it's traveling over fiber optic cables, old copper wires, or Wi-Fi. It's designed to just work, no matter what.
So this leaves us with a really important question, doesn't it? If the internet's core delivery service is just best effort, if it's not even guaranteed, then what makes everything feel so reliable? What's the secret sauce that handles all the errors and makes sure our data actually arrives in one piece? Well, the answer is another protocol called TCP, and that's a story for our next explainer.